I just try to listen to your own words.
You're old.
We're speaking, right?
It isn't key. It's good to you.
Yeah. Good. In third grade. It's coming up.
It's neat.
That,
Maybe that was a difference.
she
Just asleep. So maybe five.
I mean, it's just
To drive in. See.
oh, that's
Yes.
like yeah, it was like moving like being a sleeper. But then it's just feeling like the parents are like,
This morning.
at all. Like and then one of her friends is still like struggling a lot emotionally. Her parents were like, yeah, she's not really up for sleepover. So like yeah, she seems just to be a little bit behind the curve with just overall. We kind of knew friend who likes to track satellite. Okay, well this way we're not excluding friends who want to come. It's yeah, so we're gonna have like 6 girls.
All right, it's 8:30, and I already told Carlos this is out of his time. So I just wanted to take a moment since it's our last day, and I think many of y'all have sort of heard the story already as to how we got here. So I wanted to single out, Susanna will get here eventually, so she'll miss this part, but I wanted to single out Susanna for coming up with this idea in 2019. So I don't know if you guys know how this works, but basically, if you have an idea for a workshop here at the Institute, then you put together a presentation, you show that you've done your homework, you got a SOC, everybody's psyched, you present this to the science staff, they go off and vote on it, and if it's a really good idea, then you get to do this. And so in 2019, we basically got permission to go ahead with the 2024 calibration workshop. Everything was set. People were registered. We had all the talks lined up. The agenda was ready. And then, of course, the pandemic hit. So we just had to cancel the whole thing. I mean, literally, we shut down on Friday, the 13th of March. And we were going to start this on St. Patrick's Day on the 17th, the next Tuesday. Right. So done. So Susanna really deserves a lot of the credit for this whole thing because she got the whole thing started, organized the SOC in the first place. And I'm very grateful to that. And I was very happy to help as her deputy, but she did most of the hard work. All right, so fast forward to a year ago, and Annalisa decided that it was time that we do this. So she recruited me to help her, but again, did most of the work. And so I think we should thank Annalisa for making what's been a very successful workshop possible.
It's not true that I did most of the work. I did a lot as well.
The trick is,
Without him, I will never have made it.
the trick to being a successful deputy is they don't know they did most of the work. All right, but here's the thing. None of this is possible without Shemaya, who has been making sure that we were on top of everything. Yes, and so she deserves as much credit, I think. Everybody knows her from all the email. Here she is. And as you all know, we were sort of the test pilots for the new auditorium. And since I have the microphone, they haven't taken it away yet. I want to just recognize the heroism of Kevin Flynn in the control room back here for keeping us going. Please don't relax yet. And then finally, Annalisa and I were able to delegate a couple of tasks. Svea Hernandez took care of the posters for us, and I think that went pretty smoothly, and I'm very grateful for that. And Carl took care of the Wednesday SDAS as well, and I'm very grateful for that. So. And the microphone has been taken from me. Yeah. And thank you all.
Okay, I will start by adding another line of thank yous.
But let me do the introduction first. Welcome to the penultimate session from this wonderful calibration conference. Our first speaker today is Carlos Alande Prieto, and he will be talking to us about the potential of FLUX calibration.
Thank you very much. I'll start by adding another line of
Dana has entered the building.
Cheers.
So personally, I would like also to thank all of the organizers for a perfect meeting that, in which I have been learning a lot. And I've been charged for talking about the potential of cool stars for FLUX calibration. They have been used a lot. Is that what?
Pointing at that one.
Oh yeah, to pass, right? It's not new at all. We have seen that have been used in the past a lot, but I would like to make a fair comparison with other types of calibrators. And I will put the focus on what interests me the most, but I'm aware that also a lot of you are interested in this, which is the part of the spectrum between 3,000 angstroms and 10,000 angstroms. And I will also focus on relative FLUX calibration, not decide about the absolute 0 point. And at the very top here, what we have is mainly the sources of the data that I will be talking about later. Here, the sponsors of some of the funding that fund me. Okay, FLUX calibration, as I said, I put the focus on relative spectrophotometry. We've been talking about this for the last few days. We need at least a source with a true spectrum that we know, and the knowledge about that spectrum can come from laboratory sources that we trust, and we think they do exist, but they are hard to couple to the telescopes properly, or it can come from a model that we trust enough, and that's difficult, right? Because we know of the very many approximations that we do when modeling anything on the sky, stars in particular. Good thing is that some stars are pretty smooth and stable sources, but of course we have to deal with all of the things that we have been talking about, like instrument response, that's changing with time, atmospheric transmission, which is a nightmare, and interstellar extinction, among other things. Ideal calibration source for wavelength calibration, well, we need something with sharp lines, but for FLUX calibration, the ideal is a flat lamp like this or a flat source. They do exist. We've been talking about the last few days. We've been hearing about it. And hot stars will have a smooth spectrum that lines to the blue. Cool stars, on the other hand, will have a much more rugged shape, which can be a problem, and they line to the red and the infrared, right? Just thinking about what things we should consider when choosing a spectrophotometric standard for relative FLUX calibration. We want probably a smoothness of the spectrum. In the end, we're going to have to deal with something that hopefully will also be smooth, which is the response of the instrument. And to model that, we'll use some sort of functions. And smoother, the easier to find the fewer parameters to fit. We want them to be easy to model so that we can perhaps use these models as a reference. We want the source to be stable as well, free from extinction, or if it's not free, at least being far away enough that is beyond the extinction layer, and then we can use maps that exist based, for example, on infrared emission or H2 to get an idea of what the extinction is. And well, ideally, they will be abundant on the sky so that we don't have to point the telescope back and forth to different positions on the sky and lose time and make Ken Freeman angry. Smoothness. Well, photoionization dominates the spectra of the hot stars, in particular hydrogen for A types, B types, and F types. And this, well, means smoothness. We see here the model atmospheres, density versus temperature for an A-type star, for the Sun, and an M dwarf. And here we see, well, for the string cases of the A-type star and the M dwarf, we see here at a reference depth in the atmosphere where most of the flux escapes or begins to escape in the continuum. We see here the opacity. The dashed lines in red or blue is the continuum opacity, so bound free and free. Then we see on top of that the additional opacity from the lines. And what we see here that the dash and the continuum line for the A-type star are very close. So the continuum is dominated by these photoionization edges, and then on top of that we have the hairs of the lines. On the other hand, as we move cooler, for example, to the Sun, then we have more and more atomic lines from low ionization stages coming in, and that gives more hair. And by the time we get to the M types here, we have lots and lots of molecular bands that separate the line or the contour, the bottom of the total opacity from the true continuum opacity. And of course, this means that the shape of the spectrum is much more complex, much more harder to model. And that comes to the next point, which is which ones are amenable to modeling. Of course, we've heard it from Ralph just a couple of days ago. It doesn't get any easier than white dwarfs and hydrogen white dwarfs. It's the simpler element in the universe, and of course, the classical calibrators are DA white dwarfs, A-type stars, metal poor F types. F types have a little more atomic absorption, but then they compensate with having lower metallicity, and these stars are very abundant in the halo because of the turnoff is bluer due to the lower metallicity than in the disk. And well, here we have examples of how we can fit with models Sirius from a vast range within the spectromagnetic spectrum, a solar-like star, and an N-type dwarf. And what we see here is immediately that we do much better with these ones than with these ones, of course, than with these ones. Local thermodynamical equilibrium was mentioned also a few days ago. This hypothesis is built in most of our models, and is favored when we have higher densities and when we have cooler temperatures. So in that sense, cooler stars have an advantage there, especially dwarfs with higher densities, because they can be modeled properly in LTE. On the other hand, surface and homogeneities, the cooler stars have convective envelopes, and that makes complex surfaces due to convection. They also have more magnetic activity, spots, and what about stability? This is from Hipparchus, the fraction of variable stars. Blue means very little variables. Red means basically most or all of them are variable. And what we see here is again, that over here, we have everything, but then we go to the cool end of the main sequence. Most stars are stable, which is good. Of course, some of them, the magnetic ones, will have some variability, but those that are quiet and old will not. And on the other hand, on the cool end, but on the lower gravity, the giants are the worst for that. And there is, of course, a new version that we've been hearing about also in this conference from Gaia, made by Jesus Maiza Pejaniz. And it's a similar conclusion, but with brutal statistics. Extinction. Well, this is a nuisance for most of us, but although there's interesting physics and a lot of things that we can learn from studying extinction, but of course there is a lot of confusion with which law to apply. Then also the reference number for EV minus V, for example, should we be taking for 2D maps, for 3D maps, which one of them, because there are very many of them. I think somebody needs to put some order here and find some critical tests that made us do the right choices with this, but ideally, of course, it will be avoided. And for that, we have white dwarfs, but also cool stars, you know, giant main sequence, cool stars will be nearby, and they have very little or no extinction, right? Or the other lesser it will be go to the giants, for which we can know that at least most of the vast majority of the extinction is foreground, and then we can use reference values from other measurements, external data. What about abundances? Well, the initial mass function favors low mass main sequence stars. Also, luminosity helps giants, right? And then we've seen how in the infrared surveys, giants become necessary, the choice, because of they are the ones that are only the ones that are available bright enough. Whereas hot stars are, you know, rare in that sense, and they tend to focus especially on the main sequence on the plane of the galaxy, where most of our surveys avoid. So I come with all of these ideas. I come to this table in which, well, smoothness I take that prefer the classic calibrators, easy to model as well. Stability, well, some of the cool stars, you know, the dwarfs can be used perfectly. Extinction, well, if we go to the dwarfs, we can also use them. And abundance, and that favors also these cool stars. And I could finish my talk here, but I think I have some more time. So, and you would like more information of things that you haven't heard before. And so I have done some quantitative tests to support or refuse what I have discussed in the previous slides. So what I did was, well, let's see and be more quantitative here, take the CalSpec data and fit it. And for that, I took this simple tool called, it's a Python wrapper of the SyncSpec code for spectral synthesis from Hubeny and Lanz. It can do spectral synthesis models, taking models from Kurucs, Marks, or Phoenix. And well, it makes your life easy. Right? It can allow you to compute grids, like for example, the Bosch grids that Sabolj is going to talk about after me, or a little bit after me. It's on GitHub. You download it. Because it depends on SyncSpec, you will need a Fortran compiler for it. But with this, we can do quickly homogeneous assessment of this, how well the models can fit the CalSpec spectra for some stars. It includes one routine that is called Bayesian algorithm in simple. And well, it simply takes a bunch of models in a package that comes with the code and computes the weighted mean and the covariance for the parameters of the model. So it's pretty easy to use. I was going to do it live, but in order to simplify that, just took a shot of how I did it. And well, it looks a lot of lines here, but I point to your attention. I just have a bunch of CalSpec files here for a white dwarf, a solar type star, a metal poor star. Then I import a couple of routines, this Bayesian algorithm and another one to just make the plot. And directly I call the file, and it knows it has a file with models appropriately prepared already for some instruments, including CalSpec, right? It's this. So yes, you give it this, and it simply fits the parameters. It gives you the parameters and gives you the errors and the covariances, and it computes also the radial velocity automatically by a sort of cross correlation. And then I use this other routine just to make this plot. It will look something like this. Any one of you can repeat what I'm doing with minimal effort. Then coming to the data. Well, we have a white dwarf here, and we see the residuals hard to see here. We need to zoom in, but it's 1% or under the 1% level. You may say, well, this is G191 P2D, so you may say, well, it's a little bit of cheating because it's one of the main calibrators. So put another one. It has a little bit of noise over here, but the residuals are again at the level of below 1% in this entire range. Hard to see the residuals. What about A-type star? Pick Sirius. Why not? It's your favorite. And again, here we can see more the residuals. but again, the fit is quite good. The metal poor star, this is BD plus 174708, the so-called SDSS standard. And now the residuals, you see them again prominently here. There are some imperfections here and there. This is 18 Scorpio, the solar analog, nearby one, so we don't have to worry about reddening like the previous ones. And again, but the residuals, again, are clearly visible at this scale. And then I picked also a K-type giant, which is gravity around 2, 4,400 Kelvin. And here we see even more notable imperfections like here and here. But this star, of course, is farther away. We talked about it earlier. So if we put a little bit of reddening, just change to a grid with reddening as a free parameter, then you get a better fit. If we look at the residuals closely to find, okay, this is what we get for the white dwarfs, so well under 1%. Then on top of that, we put Sirius, and now we see that there is already a significant degradation. Then the metal poor star, thereabouts. And then the solar analog that we know, that we like, that we fit well, because of course our models are also especially tuned to the sun being what it is. And we see again a growth and in the residuals. And finally, the K giant, for which we see the scale keeps growing. And all of them, if we put the RMS here, we see versus effective temperature, we see here the white dwarf, A types, F types, metal poor star, F types, solar types, something like that. So this kind of verifies or supports what we were thinking from the literature, right? But on a homogeneous scale. Well, another test that in passing, you may think, well, how these models compare to the ones that are come with CalSpec assigned to these very same stars. I did that test quickly. Well, they do in some cases better. This example for the white dwarf, despite this blue model being fundamentally worse than the one, because this is from Koster, so it's an LTE model, whereas the other one comes from Hubeny, and I think it's a non-LTE one. And here, I don't know if I made a mistake or not. This is for the K giant, and it appears that maybe the choice is not optimal, or maybe I made a mistake because I produced this plot yesterday at night. And again, here for Sirius also it improves. Another aspect I would like to talk, another data set is Gaia XP data, for which we can also do similar tests with CalSpec. It's a massive data set. We've been hearing about it. Very low resolution, covers 330 nanometers to 1,000. Low resolution, over 200 million sources. And well, I have two postdocs that are funded by the National Academy of Sciences of China, working at the ISC on this, Xianhao Ye and Wenbo Wu, and they have been fitting this spectra as if they were spectrophotometric normal with high resolution, right? Yes, using like a fitting code, and they get parameters from these stars, and they then choose the ones that they have enough signal to noise to trust the parameters, and but they end up picking up like 70 million they trust. They compare those that have apogee parameters, and well, the agreement is fair with these uncertainties, which are quite good, I think, for this resolution of the data, right? 150 Kelvin, 0.4 dex in gravity, and 0.2 dex in metallicity. And here, what they do is then they take the ratio of the fittings, the models. I should say also that this is restricted to stars between 4,000 and 7,000 Kelvin. And they take the ratio of the XP spectra to the models, and then what they find is that there is a pattern of this weekly pattern that correlates with the type of the spectrum, the color, and with the magnitude quite tightly. And well, this is well known and is associated to the representation used for this spectra with the basis functions. And also, I should say that there is another study, I think from last year, from this year, by Huang et al., in which they compare XP spectra for CalSpec sources with CalSpec, and they arrive at similar patterns. So, well, this is how the degraded CalSpec spectra at the resolution of Gaia compares to the Gaia XP data for some stars. And well, here it's hard to see, but we see here several curves, and the original ones have a little bit more wiggles in some places than the corrected ones. And what we see here is also that the RMS comparing between XP and CalSpec at this resolution reduces from about 2.2% to about 1.5% if you do this. But what about cool stars, right? Well, we see also here the same thing with the models. And what about cool stars? And we split here the sample between stars cooler than 5,500 or warmer than 5,500. And again, we see that the cool stars, even before and even after the wiggle correction, still they fit worse, which again aligns with what we expect. And in the last part of the talk, I will also like to talk about DESI, which is these days the main sink of time for me. And well, you know, DESI is like an extension of what Sloan did before, with many fibers, spectroscopy, to doing BAO on the sky, and it's a very complex machine with 5,000 fibers, a robotic positioner, moves all of the fibers at the same time, so it's quite fast. It is all operating on the Kitt Peak observatory at the Mayal. The fibers have 1.5 arcseconds, so with the typical thing at Kitt Peak of about 1 arcsecond, you know, it's a bit tight to do spectrophotometry, but it has an atmospheric dispersion correction, which is something that normally these kind of instruments don't have. So there has been a big hope that the spectrophotometry could be at least useful. These are the 10 spectrographs, each with 3 arms that all of these fibers feed. And so the requirements for the cosmology, for the BAO, in terms of flux elevation are not very tight. I think 5 to 10% is plenty for them. But of course, they also do stars, and for us, it will be a source of a lot of additional information, for example, on effective temperature. So I'm very much interested in this, and I cross-match CalSpec with DESI. In 3 years of operation, there are already like 10 million stellar spectra taken, and well, I found like 9 of the CalSpec stars were here. This is a couple of examples. A lot of them look like this. This is a solar-like star, SNAP2. What we see here is in blue, CalSpec. And now in this case, I have a smooth DESI spectra because they are higher resolution to CalSpec. But the DESI spectra, because there are 3 arms, I plotted in 3 different colors: orange, green, and purple, red. And what you see here, I didn't take the ratio, but it's quite good. It's at the level of 1-2%. But on the other hand, for example, for this white dwarf, and there are also many like this, there is nearly perfect agreement in the infrared and the red arms. But on the other hand, it shows also that in the blue side, we need to do additional work. And well, I should say that the calibration is based only on F-type dwarfs, subgiants, in the halo, but they also observe a lot of white dwarfs. This, as we discussed yesterday, could be a great source of really tens of thousands of white dwarfs for creating a network that ideally would be tied to the CalSpec system. And they also have A-type stars, a lot of A-type stars, not because they are interesting scientifically, but we included them on purpose for calibration as a check. They are not used, so they can be a very an excellent test of the results. And with that, I come to the summary. That I think the only advantage, at least for this particular purpose of cool stars, is that there are many of them. That the dwarfs are stable and nearby. Of course, they have more infrared flux, so in the infrared there will be the obvious choice. But at a resolution of about 500, 1,000. And of course, higher resolution, the worse, the more dramatic this statement. The classic calibrations clearly do better, 1-2%, whereas cooler stars like solar-like will only do 3-4%, and K-type stars even worse. Of course, at much lower resolution, you smooth your spectrum, especially if you don't need to trust models for propagating your calibration. It should be fine to use them, and especially the dwarfs for photometry, there shouldn't be problems if choosing them correctly based on for example, the Gaia variability information or the many satellites missions that we have doing the planets these days that have ultra high precision, right? And this is all. Thank you.
Thank you. Finished early even. Questions?
It's okay. I don't have a microphone. So, Carlos, nice talk. I have a comment on the last point in there. So it is true that in general, dwarfs and subgiants are less variable. That's why they are more adequate for these purposes than giants and supergiants. So that's, in general, that's an accurate statement, but there is an exception, which actually you can see in the plot from my paper that you show. And those are red clump stars. So red clump stars are K-giants, and almost every time you measure them, they have very low variability. Actually, they are among the least variable stars that are known. So if you need a type of object which is luminous, abundant, and you don't mind it being cool, red clump stars are an excellent choice.
I agree, and I think it's an excellent point because also we have from Apogee a great catalog of this type of objects. So that would be another source for creating a network of calibrators for the infrared.
Kevin.
So you're saying here that at low resolution, you don't have to worry about the models being not quite correct. Is it?
Well,
I mean, in detail about the line profiles, essentially. Am I understanding correctly?
Yeah.
But on the other hand, you've got these broad bands, of weak lines, and you worry that your continuum level is going to be off in a way that will be systematic.
If the star is stable, I think then you could use them. And if we discard the M types, right, the most extreme one, and for K types and G types, we could still, the models on average, if you go to low resolution or to photometry levels, will do pretty well.
Well,
it's just the fine details.
That's what I'm asking. You're averaging over many bands, and you'll have a subtle continuum shift depending on how you on the bands in the models at high resolution before you smooth them. Well,
I mean, the thing is that the frequency of the lines, which is the hard part, especially the molecules, except for systematic errors, I think that there will be, if the spectrum is stable, then once you smooth enough, so you go to like Gaia XP resolution of 50, 100, I think it still will be fine.
Yeah, there's a question online. Ariane, do you wanna ask the question yourself, or should I read it?
Okay, I can ask it. Thank you for the nice talk, and I would like to take the opportunity to ask you, because we were talking about red clump stars. Currently, what is your evaluation of how good the synthesis models for stellar spectra are at reproducing simultaneously the optical line spectra and the SED into the infrared, like optical plus infrared? Like, can you find a model at a certain temperature and gravity that will fit the optical lines and simultaneously fit the SED out to the infrared for a red clump giant?
Honestly, I couldn't answer you, at least not quantitatively, because it's not something that I have tried to do myself.
Okay, because I've tried this, but not necessarily with the best possible combination of data and models, but I haven't found a solution to that yet. So I think that's an interesting question to dig into in the future.
Yeah. We should be doing more, panchromatic fittings where we don't neglect any information that can be used in that sense. In combining spectroscopy with very broadband, wide range spectrophotometry is source of information.
Yeah, thank you.
If there are no more questions, let's thank our speaker again. Introduction during the transfer. Our next speaker is Gerard Van Bell, who will be talking about calibrating the effective temperatures and linear radii scales for giant stars. I'll give you 5.
Very good. All right, thank you very much. It's good to be here. We've heard a lot about very interesting challenges in flux calibration. Throughout the week, we've heard interesting mentions of interferometry. Yet we have not heard from interferometry, so I'm here to be your unicorn to tell you about interferometry. So we did a project where the goal was to try and come up with the reference set for directly, and I'm going to emphasize that word a lot here, directly determined giant star temperatures and radii. The facility that we used was the Palomar Testbed Interferometer. This was a facility built in the heady days when NASA liked interferometry. I foresee a return to that because interferometry is inevitable. But this was built in the mid-90s, and there were 3 apertures on this interferometer right next to the 5-meter Hale telescope for scale. That is the 5-meter mass simulator sitting out gathering dust. But we had only 2-way combination in operation. So we had 85-meter and 85-meter baseline, and the principal baseline we used was this 110-meter baseline. Operations were in the K-band. Some operation was done, but this work was principally K-band. This was built to do astrometry demonstration for the Keck interferometer. In the end, it was really a very productive scientific instrument in its own right for doing visibility amplitude interferometry, where we were able to measure sizes of things very well. And it was almost fully robotic. We had a human tending it, but it did most of its work by itself, and so it's very good for survey work. Our original survey, which we published from this, was a set of about almost 60 giants. A lot of it was single epoch measurements. We didn't really understand things, and I think we had pretty poor calibration on things. More importantly, I think we had an underappreciation of the necessary ancillary data. Importantly, the bolometric fluxes that we wanted to calibrate to basically get us good temperatures, because in the interferometry world, if you get an angular size and a bolometric flux, the temperature pops right out as a direct measurement. And so we had a number of things we weren't doing very well, and then we had the old Hipparcos distance at the time were this treasure trove that had just been blessed upon us in that 13-volume set that we may all remember, including volume 13 with all the seeds. I still have it on my shelf. So in the intervening time, we've thought a lot and worked on improving the SED fitting. Here's an example one. I forget what this translates to, gamma something. This is a supergiant that we did, where we tried to use the narrowband and broadband photometry that was available in the literature to try and come up with a bolometric flux, basically the area under the curve here. And there's been improvements over the years in terms of the empirical templates that are out there, but also the model templates that are out there. And it's good to run these against that's basically the blue line in this fit, and do some true reddening fitting as well on this. So overall, my colleague Andy Bowden has been curating this code for the last 15 years or so, and it's really well tuned for coming up with the bolometric fluxes needed to get us good temperatures from these angular sizes. In the end, the funny part is the angular sizes is where all the technology goes in, and you have delay line carts running around on rails, and you're positioning mirrors to a nanometer, and that's actually the easy part. In the end, the hard part is this bolometric flux work. So we thought a lot about how to improve this whole approach. A lot of additional follow-up observing has started to really kind of come into play with using the archival Palomar data that's now out there. A lot of it is very narrowband work where the stars are fairly bright, and that helps out a lot with being able to use very narrow bands that are amenable to both tuning into certain features on the spectral energy distributions to get very nice fits and very unique fits against certain templates and against certain spectral types. it's also fairly immune to variations in atmospheric seeing. And so that helps out a lot. Limb darkening has been improved a lot, I think. It's a fairly parasitic fit at this point. And importantly, we understand the instrument better. We have the systematics are better understood. We have a much better point source catalog. And for the targets that we observe, we have many, many nights of observing. And so that beats down a lot of noise as well. Distances are a little better. They're still terrible. And this is because they're bright stars. The Gaia work is not very good on this. Hipparcos work was not very good on this. Particularly for the redder stars, we have lots of pathological problems with surface features on the stars that move around on year-long timescales, which is the timescale of the parallax measurements. And yeah, it's kind of a mess. So distances are better, but they're not a whole lot better. So initially, if you want to plot the linear radius that you get from the angular sizes for these, that's the first thing you want to do. And you can kind of decompose what the spectral type is for these things. And, you know, it's interesting, but it's not really that compelling. More compelling is where we really have a lot of accuracy, I think, and that's in the temperatures. And so what we have here is all 191 stars, so a much bigger data sample than our initial survey of not even 60 stars. And a good index that we have found to throw this against is a V-K color, a de-reddened V-K color. So one of the neat things about these SED fits that we're doing is that we're able to come up with indication of how much to de-redden both the V band and the K band. So we come up with a homogeneous scale along the horizontal axis. And we range all the way from the hotter giants, G0, all the way down to very, very red giants, the M8. And we have what we think are pretty good uncertainties for a direct measurement. It's actually sufficiently interesting that when I was looking at this data set, and this betrays actually my ignorance with a lot of things for star evolution, so I thought about this way too much, was seeing where the data wasn't. And so if you zoom in, you can find spots where there actually appear to be places where you could drive a truck through here. And, why are there not any data points here? It could just be random distribution. We did some Monte Carlo tests. It looks like it's, marginally interesting here. And the right answer is, in fact, there's some physics going on here. And so if you take our data and you throw it up on an HR diagram, these are all of our data points. We went ahead and color-coded some of them that also turn up in a catalog as red clump stars, and then throw on top of that an evolutionary track. If you follow these tracks both up to the where the helium shell burning, and you have the helium flash, and you drop down to the red clump. If you look at the tick marks here, these little triangles, this is a great confusogram, by the way, where they all pile up, where the stars basically slow down and pause for a while they're on the red clump. This is where they spend a lot of time. So in this plot that we were just looking at, you're going to get in temperature space, you're going to get pauses where you jump across these gaps, really, if you look at the time ticks on here. And so it's actually not surprising that you would see these gaps where the stars are not likely to turn up in temperature space. And so what's neat is this is HR diagram, like I said, fully empirical HR diagram from these direct measures of bolometric flux, these measures of the angular size, and that getting you to these temperature measures. It's one of these things where we want to get to the place where you try to come up with these sorts of graphs in a as model independent way as possible. It's not completely free of that sort of intervention with little things like limb darkening corrections and so forth, but it's pretty clean. And so this is nice because this is the sort of plot that you can throw back at theorists and make them think about how to get their temperatures tuned right, and think about how these tracks match up with the plots that we have here. So go read the paper. It was a little long. It's mostly tables. But yeah, it was a pretty big paper, and reflects 15 years of work all in one giant data dump. Where we are at now is still continuing to do more work. We're still trying to improve both the photometry and these SED fits. We have automated telescopes doing this work. I have my favorite thing right now is my half-meter telescope with narrowband photometry across 13 bands from 520 to 940 nanometers. The bands are 10 nanometers wide, and they're really designed to try and nail down this stuff. These are all flux calibrated against NGSL, and so the observing is very much focused on calibration. So about half of the time is interleaved observations between targets of interest and then HST STIS stars to really nail down the flux as good as we can. Right now, a project we're working on is there were supergiant diameters that we published in 2007, and great diameters, terrible fluxes. And so we're working on trying to redo the flux calibration on those sources and come up with an empirical temperature scale for supergiants. And that's in process right now. And we're trying to think about ways to even get more fancy with the SCD fits. And we also have NSF funding to look at MIRA variables. We have over the 10 years that we roughly operated the Palomar instrument, we kept on revisiting these MIRAs. And so there are some of these MIRAs for which we have, on the order of 100 epochs where you can see the angular size varying by 20% for these stars. And so now we're kind of trying to come up with matching bolmetric flux data for that a little bit after the fact. So it's a bit of a mismatch, but we have some very interesting data on that that's letting us really poke at what still seems to be kind of unexplored space for these MIRAs. People hate working on MIRAs because they're so dynamically complex and they really defy the stellar modeling. But we, with my collaborators, Michelle Creech-Ekman and Dana Bayless at New Mexico Tech, we're taking a good run at this, and we'll have those publications coming out over the next year. With that, I will take questions, and interested to hear what people think of this work. Thank you very much.
Questions?
Got one over here.
There's one online. You can go ahead, Ariane.
Okay, hi, I'm taking the opportunity again to ask questions that I'm really interested in. Thank you for this talk. Yes, you mentioned red supergiants at the end, and in some recent work where, again, it was about comparing how well models do at reproducing optical molecular band spectra of red supergiants together with the SCD. Some people came up with the conclusion that you need wind loaded with molecules to explain all this together. And so my question would be, in that context, do you already have an idea how to interpret radii? You talk about radii, but it's a very complex thing for red supergiants.
Yeah, we spend more time than you would think thinking about radius and what does radius mean? What is radius at a wavelength? What is a radius in a wavelength integrated sense? Generally speaking, we work on Roslin mean diameter and try and come up with basically a wavelength average radius. The one thing that's pretty forgiving about this work is it being done at 2.2 microns. It does tend up to actually be pretty reflective of the mean photospheric radius, which is the element of interest here to get at the temperature. And so, it's still, even internally, a source of heady debate. Yeah, we find that it's at least better behaved than the visible diameters for these stars, which can vary and can be often contaminated a lot by the surface morphology. The near-infrared stuff is a little cleaner.
Thank you. Yes, I agree with that. Thanks.
In the back.
Yeah.
Hi, Chuck.
Gerard, thank you very much. I was struck by your comment that you understand PTI better, only because the survey is not operating. So it kind of was interesting to me from a sociological standpoint. Is how difficult has that been to better understand the systematics when you're actually not there working with the hardware?
So we understand it better from the basically the data standpoint. Okay. Astronomers are terrible at statistics. And so my ace in the hole was, yes, there are two of them. My father is a statistician, and so he actually helped me with a lot of analysis on looking at the data and looking at calibrating calibrators against each other, looking for areas where there are obvious outliers. This being not just a a prototype for the Keck interferometer, but also being a prototype for the Space Interferometer mission, there was a lot of telemetry here. And so we're able to dig out correlations of things. And so there was a lot of data to mine in trying to dig at that. And so we basically, since it was semi-robotic, there was a lot of data, and we were pretty unreserved in throwing away bad data. And so that, I think, helped a lot with taking what we felt were the angular size calibrations from, say, the 5% level down to, about 1%. Hi.
Question. I have a question about your empirical HR diagram. So apparently you have some M8 stars, and so you have a maximum luminosity, which is approximately going to be the value at the tip of the AGB. So what is that value, and how does that compare to the model?
I haven't looked at that specific question as far as the maximum luminosity for those M8s. And I didn't pay a whole lot of attention to that, in that these are luminosities that are connected to empirical distances. And particularly on the very red end, the distances are just a mess because of how these things are really starting to be very full of features in a morphological sense, in an appearance sense, when you're trying to look at them. That's consistent with stellar models by, say, Andrea Chivasa. And I am highly skeptical of the ability to get good parallaxes off of something that has a photocenter like that. That's going to be moving around on the time scales of the parallax measurements.
Speaker again.
Thank you.
Next up will be Zalbax Mizaros. Will be talking to us about the updated BOZ Synthetic Stellar Spectral Library.
Do you put in presentation on here? Oh, it's a PDF.
This is a PDF.
Ah, it's a PDF. Full screen down at the bottom.
Okay, can I use it? All right, thank you very much. My name is Szabolcs Mészáros. I'm from Hungary, and I have been working on this long digital sky survey in the last couple of years. So the original idea to create a large synthetic spectral library to fit the Calspec stars came from Ralph. And he contacted me at the end of 2012 or the beginning of 2013 to create a synthetic spectral library that he can use to fit the Calspec stars. So my idea was to expand on this original idea and try to create a spectral library that covers a very large temperature range, a very large wavelength range, very large composition range. So people can just use the spectral libraries to do whatever they want with it. So to cover as many science cases as possible with a large synthetic spectral library. So there are two different versions of this. The legacy version, which was published in 2017, was made using the Atlas 9 model atmospheres with the Synthi code that Bob Kurutz developed. And there's a second version here, the 2024 version, which we published this year. And we have a wonderful website that Scott Fleming made for us. So thank you very much, Scott, if you're listening, where you can download all the data. And both the legacy version and the updated versions are available as well. So what's the difference between these two different versions, or what is the overall property of or what are the overall properties of this large synthetic grid? So here you can see what the TEF range in the 2017 version is and what the TEF range in the 2024 version is. And on the right side, you can see these parameters visualized. So in the TEF log-J space, we cover almost all stars that can be observed, except for the very hot ones. So we shrinked the temperature region in the 2024 version because these are made using LTE model atmospheres, Atlas 9 and Mark's model atmospheres. So at high temperatures, they are not very accurate. And we extended the temperature range from 3,500 Kelvin to down to 2,800 Kelvin. The log G range is roughly the same. We go a little bit higher, so we reach the top of the red giant branch. The metallicity alpha and carbon range is the same in both grids. And these are the parameters that basically cover all the chemical compositions that you can observe in the universe, almost all of them, except for the very, very metal poor stars that we don't sample. So in the background on the right side, you can see the apogee observations, the SDS apogee observations, and the individual dots show you where we have a model computed. So if you calculate how many different compositions there are, you get a number of 336. So there are models for 336 unique compositions, and each of these compositions have almost 500 model atmospheres associated with them. So the microturbulent velocity changed from 2 kilometers per second to starting with 0 and ending with 4 kilometers per second. And the wavelength range is quite large. So in the 2017 version, we started with 100 nanometers. Now we're starting with 50 nanometers and with 32 microns. There are various resolutions available. In the newest version, we start at 500 and end around 600,000. And that 600,000 resolution is available in the entire wavelength range, starting from 50 nanometers to 32 microns. And there are different resolutions that you can download. A significant improvement were made in the model atmospheres that we are using. So now below 8,000 Kelvin, we are using the MARCS model atmospheres instead of the Atlas 9 model atmospheres. The spectrum synthesis was done with SynSpec that Carlos just mentioned in his talk. And we significantly increased the number of molecules that we are including in these models that are important in cool stars below usually 6,000 Kelvin or even below that. So another important improvement was to refine the temperature steps. So below 4,000 Kelvin, the models are available in 100 Kelvin steps. This is an important thing because below 4,000 Kelvin, the spectrum changes a lot as a function of temperature. So on the right side, you can see examples of synthetic spectra. So on the top panel shows you the entire wavelength range that we cover for solar metallicity, starting from the coolest temperature all the way to the highest temperature. The middle panel shows the optical range in medium resolution, and the bottom panel shows a narrow range with very high resolution. So the highest resolution available changes with temperature. So at A-type stars, it's around 200,000, and the M-type stars, it's about 600,000. There are 8 different resolutions that you can download, starting from 500 to 50,000 and the original resolution. So we updated all the opacities from the 2017 version. Most of these, or almost all of these, were calculated by Carlos and published in his 2018 paper. So there are bound-free opacities for 15 atoms and molecules. And of course, no models are perfect, and our models are not perfect either, unfortunately. One of the big problems we have is that 8.5% of the MARCS models are missing because these models do not converge when they get calculated. There is no way around this because the MARCS model atmospheres are not public, so we cannot go and calculate them. We don't interpolate model atmospheres because we would like to avoid the error that comes from interpolation. So we are not doing that. And during the publication of our paper, we noticed that an 8-level hydrogen atom was used during the calculations. So there are some hydrogen lines that are missing above 5.8 microns. So this is something that we would like to fix. And this is actually not a bug. The grid contains some extreme composition. That's not a bug, that's a feature. But that means that at very extreme compositions, the spectra will look weird, but those don't have, observed parts of the usually stars don't have very extreme compositions in nature. But anyway, so we would like to have a full grid so people can fit fit any type of spectra that they want. Another problem we have with the OH plus molecule. So let me talk about the molecules that we are using here. So in this plot, you can see the molecular absorption bands as a function of wavelength and temperature. Okay, so the most important molecules here are the water and titanium oxide. So can I point with this? Oh, okay, so that's water there. So as you can see, it absorbs a lot of light in the infrared, starting around 4,500 Kelvin. And titanium oxide is a significant absorber in the optical range. So the original legacy version had 12 different molecules, all coming from Bob Kurut. We added 12, but now we are going to subtract 1 because it turned out that the OH plus that we included is not good. We made a mistake of how we included OH plus. So this panel here is incorrect. Then we have incorrect OH plus molecular lines in the synthetic spectra. We already know how to fix this. We just need to remove OH plus from the equation and not include it in the synthetic models. So once we recompute all of these models, we will fix the issue with the hydrogen lines, the OH plus lines, and other smaller things that we found in the models. So the important thing here is that we added 12 new molecules, and all of these have, or most of them, come from the ExoMol project. So they have up-to-date atomic physical parameters. So, okay, so moving on. So what is the difference between the Atlas 9 and Mark's model atmospheres, or the spectra that comes from an Atlas 9 model atmosphere and the Mark's model atmosphere? That is what this figure shows you. This is the fractional difference, means that Mark's minus Atlas 9 divided by Atlas 9. And this is the flux difference between these two different models as a function of wavelength. Everything, all the other parameters are kept the same. So the general conclusion here is that between 1 micron and 32 microns, the average difference that is coming from the two different model atmospheres is about 0.3%. So somebody asked in the first day, thank you, first day, what is the accuracy of the stellar models, right? That's about 0.3% or worse, and that's just coming from using different model atmospheres, right? So I zoomed in here. Here you can see the very low temperature model has higher flux in the Mars model atmospheres than in the Atlas 9 model atmospheres. This is due to structural differences in the model atmospheres at low temperatures, and the same causes this UV excess flux in the Mars model atmospheres compared to the Atlas ones. Okay, so this plot shows you the fractional difference between the old and the updated model updated fluxes at 5,000 resolution. So in the entire wavelength here, in the optical and in the infrared. So I would like to point out two different regions here. So in the optical, you see these large 20 to 30% flux changes in these bands. These are due to the updated titanium oxide line list. And the other significant change that you can see here in this region, where the coolest models have about 5 to 10% higher flux in the 2024 model compared to the 2070 model. This comes from the updated water line list. So this is how much how important it is. So this shows you how important it is to use the latest line lists, because these line lists can have a huge effect on the synthetic flux that we are calculating. So we are also doing another project using this Bose grid. We are computing a large database of bolometric correction and synthetic magnitudes. So in this right panel here, you can see the Gaia DR3, the bolometric correction in the Gaia DR3G band as a function of temperature, color-coded by the reddening. And in this plot, you can see the synthetic GP minus G, the synthetic BP minus RP color, and the J minus K color. So this colored plot in the background shows you the synthetic colors, color-coded by temperature, and the contour is the common stars between Gaia DR3 and 2MASS that have very good accuracy. All right, so overall, so the new Bose synthetic spectral database contains more than 600,000 spectra. And if you download all the things that we published, then you will end up with a 12.7 terabyte database. and that is without storing the wavelength columns. So we get rid of the wavelength columns, and we saved like 2 or 3 terabytes just removing those. So the library covers this wavelength range, and we have updated model atmospheres, lines, and continuum opacities. So I really would like to thank all of these people who helped us create these models for us to allow us to create this library. Carlos worked a lot on the opacities and of course on SynSpec and simple code. Scott made the website that we use. So I also would like to thank the people behind the masks for allowing us to publish this large database on the STSC website. And all the other people helped in various stages when we computed these model atmospheres. So thank you very much.
Questions? I can just shout. I was wondering if you've compared these to any observations so far, and if so, how those look. Because this is awesome.
Yeah, so the CalSpec stars are fitted with this library. So that's one thing. And we had another paper that we published this year where we had an optical spectrograph at a resolution of 18,000, and we observed cool stars and fitted them. And these stars have very good parameters. So we derived abundances of certain elements, temperature, log G, and compared them with the apogee data, and everything lined up within errors. So I'm fairly confident that this library performs well, even in abundance analysis.
Line from Ariane, and then another one.
Hello, me again. Yes, I was wondering, I mean, this is fantastic to have all these spectra available. The thing is, it's a practical problem to download them and do fitting in such a database. So is simply the tool you would recommend to, when you have some data and you want to fit it against all those models to find the best one? Is there a tool available that avoids having to download all the data?
Oh, there are, on the website, you can download different resolutions and different chemical compositions. So you can just choose like solar composition and download the spectra that have 500 resolution. So that will result.
You don't have the opposite, like upload a spectrum, upload one data. Typically you have one spectrum that you want to fit, and downloading terabytes of data just to fit one spectrum is whatever, even if you take only a quarter of it. But do you? So
you don't have to download the entire database.
No, but you don't know.
You don't have to download the entire database. So you can choose resolutions. So say you have, a 15,000 resolution spectrum, you just download the 20,000 resolution version and convol it down. And if you know roughly the composition of your star, right, then you can also choose a grid that is close in metallicity and just download that grid.
Still, you have to,
so you don't have to download 13 terabytes of data to use the.
Anyway, the question was, can I upload my data?
I'm sorry, I don't understand. So,
do you have a tool for fitting?
Oh, no. I mean, not on the website. No.
Okay, thank you.
Everett wants to ask a question. Shall I read it? He's asking, are limb darkening coefficients calculated and available as well as the spectra?
So are the opacities available?
Limb darkening coefficients.
So that's explained in Carlos's paper in 2019. Sorry, 2019. Sorry, 2019. Yes, yes, you can download all the data from the simple GitHub website, right, Carlos?
Not limb darkening.
Not the limb darkening.
Cannot be computed.
Oh, okay. So, but the opacities, yes. So.
Question about, I don't hesitate. I hesitate a little bit since it was really awesome to get out to 32 microns for JWST, but now I'm beginning to wonder about Prima, which is starts at 23 microns and goes longer. So how possible would it be to go to longer wavelengths than 32 microns? And is there any limitations? Is there any, other than space considerations, et cetera, that would stop us from computing this out at some way?
No, it's only the question of how much computer time we have and how much space you have. But we can extend the longer wavelength range.
Is that possible to be done in a delta way? Like later we could say, okay, we really want out to 100 microns. Is that possible to add an addendum? And then
so you mean patch the spectra up? Yep. So just calculate from 30 microns to 100 microns? Yes.
Okay. All right. That's very useful. Thank you.
Yeah.
Last question.
Question as well. So are volumetric corrections also available for all spectral types, and like mostly I'm interested in HST filters?
So not yet. We are still writing the paper about the global volumetric corrections and synthetic magnitudes. So that's not available yet. I'm hoping that next summer is the date when we can publish it. But we do want to recalculate the grid first to get rid of the OH plus problem and get those missing hydrogen lines. So at least we can have all the hydrogen lines in the spectrum. And then we go and recalculate the volumetric corrections, synthetic magnitudes again, and that's when we will publish that data.
Okay. Next summer.
Yes.
I take on your word.
Yeah. Thank you.
Oops. Thank our speaker again. Our last speaker of the session is Abigail Elms, who will be telling us about a network of cool white dwarfs as standards for flux calibration.
Thanks. Right, okay, thanks for that introduction. So yeah, I'm Abby Elms from the University of Warwick, and I've been working with all these great people here on the slide to build a network of cooler white dwarfs as infrared standards. And I should mention that all the work that I'm going to be talking about today is at that reference there on the bottom right, because the paper got published last week, which is great. Okay, so you might be asking, why do we need cooler flux standards in particular? Because we've got 3 hot primary standards that are all above 30,000 Kelvin already. We've heard a lot about them this week. They've got a approximately 1% consistency with the HST flux scale. And you can see in the plot from Ralph's 2020 paper, the residuals there for the SED between the data and the model, which is great in the optical. But the accuracy just reduces to just above 1% in the infrared. And of course, these uncertainties propagate into results, which isn't great. And some of these are too bright for JWST observing modes. So cooler model atmospheres from UV line blanketing, sort of like complex NLT effects, which creep into the uncertainties for hotter white dwarf models. Their energy distributions peak in the optical and the infrared, which is great if we want to calibrate in the infrared. There's a larger sky density, so we've basically got more choice. And they're generally closer than hot white dwarfs, so we've got less or negligible reddening and more precise Gaia parallaxes, which again reduces the uncertainties there. So I probably don't need to motivate this slide too much because I'm pretty much preaching to the choir here with this audience. But we want precise infrared observations for cosmological measurements especially. So looking at type 1a supernova fluxes, looking at exoplanet studies, things like that. And of course, we're in a great era right now of space missions such as JWST, ELT, Euclid, and Roman, which are all going to get us really, really great infrared data. So it would be great if we could have standards that are going to be as accurate as possible for those. Okay, so our network consists of 17 DA standards. So they have all got effective temperatures less than 20,000 Kelvin. They'll provide an estimate for infrared SEDs, set precision, on infrared calibration. We use HST spectrophotometry from STIS and WFC3 with the gratings shown in the brackets, and I've just put the plots of the throughputs there. I should also mention that we have had recent networks of faint DA standards with temperatures larger than 20,000 Kelvin, so hot standards, and they are in good agreement with the HST flux scale in the near infrared, which is absolutely fantastic. But there are advantages of cooler white dwarfs, as I spoke about. So just a little bit of context, as I appreciate I'm not speaking to a white dwarf community audience. So we have chosen the 17 white dwarfs, and I've put the distribution there in galactic coordinates. There's less than 4 hours between any two white dwarfs, so we've got a good distribution across the sky. To put it into context of all of the high confidence Gaia white dwarfs, there's 359,000 of those. So of course we've got a lot of choice in our white dwarf standards, but we have to put some quite strict constraints on them, as we know. I will not take the credit of choosing the 17 white dwarfs. That was Pierre and Ralph. Had to sift through all of those Gaia white dwarfs, so I sort of swooped in and did the interesting work at the end. White dwarfs in Gaia have got a temperature range from around 3,000 to 140,000 Kelvin, but we're just looking at the cooler end below 20,000. So those are the WD numbers of the 17 white dwarfs in the network. They're all in the paper. They are easily copy and pastable into Simbad. If you want more information on them, I've got the Gaia DR3 designations in the paper as well. Again, copy and paste that into Gaia if you want the astronomy. And I should also mention that two of these white dwarfs, so 1327 and 2341, were previously analysed in 2020 as infrared flux calibrators, and they were found to be consistent with the HT flux scale. So what this work has done is basically built on that. So what did we do? So we fit the STIS and WFC3 spectrophotometry of the white dwarfs with the latest 3D DA LTE models from Pierre-Emmanuel Tremblay. So these were models that were updated in March of this year. The URL is at the bottom where these model grids can be found if you're interested in looking at those. Some of the updates included wavelength coverage between 40 and 600,000 angstroms. The wavelengths are now in vacuum wavelengths, and we do have the option to use H2 molecular lines or not. For this particular work, we did not need to use them because we're using low resolution STIS. But if, for example, you guys have got high resolution UV data or something like that, then we'd recommend using the H2 molecular lines. We fit using two different methods. So method number one, we did an SED fit of the continuum and parallax, not including the Balmer regions. And the second method was only fitting the Balmer regions. So this essentially gave us two independent effective temperature and log G values, giving us model absolute fluxes. For the fitting, we gave our observed fluxes, compared them to model Eddington fluxes using this equation. We allowed TF log G parallax E B minus V as free parameters, dealing with chi-squared minimization, used the 2020 DA mass radius relation, reddened using Cole Gordon's G23 model. We did not fit the Lyman alpha region, so we started at 1,450 angstroms to remove the uncertainties there in the UV. Just to note, the two coolest white dwarfs, we had to start at 1,700 because the Lyman alpha region sort of creeps into redder wavelengths at decrease in temperatures. And to avoid the end of the filters, we ended our fits at 16,000 angstroms. And of course, we masked the Balmer lines. So we got statistical uncertainty straight from the covariance matrix of the fits. We calculated systematic errors on our fits, and we did this by fitting just the UV and then the combined optical and infrared regions separately to get two different values of TF and log Gs. And then we did a log likelihood maximization technique, which was quite complex, and there's lots of equations. They're all in the paper if you want to read that section, if you're interested in the statistics of it. But essentially the results were we got a 1.1% error on effective temperature and 0.01 dex on log G. Okay, so these were the results. So we successfully predicted the fluxes within 3% over most of the range that we fit. The median standard deviation flux residual for all 17 of the white dwarfs was 1.41%, which was really good. This even crept down to lower, to like 1.15% when we just fit the optical and infrared, so didn't do the UV at all. But just to mention, for the coolest white dwarfs, the residuals do creep closer to 3% just because of the uncertainties with modelling the coolest white dwarfs. And here I've just put one of the results. So in the top panel, we've got the SED, the black line is the data, the red line is the model. In the bottom panel, we've got the residuals, and then sort of like the blue panels are just those regions that we didn't fit. And if we look at the second method, we fit the Balmer lines, again, very similarly, using chi-squared minimization. We fit effective temperature, log G, radial velocity, use the same mass radius relation. But this time, to get the most accurate models possible, we convolved to the line spreads function of the instrument. And these can be found on the Space Telescope website at the URL at the bottom there. But we basically found that if we fit to the LSF, it just took ages, and it was super complicated. And as we want to roll this out to like SDSS5 foremost, it just wasn't going to be computationally feasible for doing this on like hundreds of thousands of stars. So what we did instead is we fit 3 Gaussians to the LSF to create a quick, as in like less than a second, and computationally feasible LSF function, which was accurate to well within 1% of the LSF. So that was more like of a practical way of doing it. Just to mention as well, we did not fit H alpha because that was on a different grating to the higher order Balmer lines. So that would have introduced uncertainty there. And also, like I mentioned, some of the bigger surveys are actually going down this route as well of not fitting H alpha because of the added uncertainty. The higher order Balmer lines do a fantastic job as it is. And just over on the right there are the fits of the Balmer lines. Again, black is the data, red is the model. Can't really see the black data very much, which is great because the model fits very well. So when we get our 2 independent TF and log G values from our 2 different methods, if we plot them side by side, we should get a straight line. If we plot them, we fit a straight line, and it works really, really well, which is great. This is exactly what we want to see. For the effective temperature, 16 out of 17 stars are within 3 sigma of each other, 8 stars are within 1 sigma. For log G, 16 out of 17 are within 1 sigma. So this is a really, really good result. So just to put this all together, these are what the plots look like in the paper of everything all together. We've got the SED and Balmer fit parameters there, which agree very well. And this is for the hottest star in the sample. To go on the other end, this is the coolest in the sample. You can see straight away that the model struggles at bluer wavelengths. So you can see we've not fit a large portion there, but in the redder optical and infrared, it still does a pretty good job. Also to mention, this star and the next coolest one, so the 2 coolest stars in the sample, the models won't be available on CalSpec, but they will be available in the electronic distribution of the paper if your source, if your science requires you to have a cooler calibrator. We also fit 4 synthetic magnitudes and compared with Gaia 2 mass and Ys. I'm just showing the Gaia ones here. We did the GBP and RP filters. We integrated under our best fitting models, again, corrected for reddening. And we combined the observed and synthetic errors here. And we found really good results of all 17 stars being within 2 sigma and 14 stars being within 1 sigma, which is, again, a really, really good result. So just to conclude, we have got 17 DA white dwarfs that are cooler than current standards, so less than 20,000 Kelvin. 15 of them will be available on CalSpec, 17 of them are in the electronic distribution of the paper. We modelled them with the latest grid of LTE atmospheres with 3D convection. So that is another advantage to perhaps like a decade ago where 3D convection wasn't included in models. We reproduced the HT flux scale within 3% from UV to near infrared. Our TF and log Gs agree within 3 sigma. And for the synthetic and observed Gaia photometry, they agree within 2 sigma. All models will be available on CalSpec. Ralph is just tweaking the FITS files. So they will be on there soon, so watch this space. But if you need them now, if you go to the MNRAS distribution of the paper, they're there in a zip file, just click on them, and they are in just a text format. I do have them in CSV, so please email me if you want them in that format as well. Okay, and with that, I will take any questions.
Kevin.
So if you go back to your comparison of so there seems to be a small systematic between your results and. Do you have any idea why? I mean, I know it's hard to get Gaia to work at this level, but I'm interested in what you might think.
Yeah, so good question. So we did flag that as well, and this has been seen in other studies that have done the same. Short answer is no, I don't know what it is. We can do more digging into it with the RP band especially, but short answer is we can do more work on this in the future to sort of dig into this, but essentially for the paper, we didn't want to highlight any issues with Gaia, so we kept quiet. Yeah.
Yes. So there's a question online. Do you want to ask that now, or you want me to ask it? I can ask it then. So on slide 13, the ultraviolet part doesn't fit well. What is the reason? Temperature is off. Is there any hope for sub-percent level prediction?
Yeah, so because this is an 8,500 Kelvin white dwarf, as we go to low temperatures, basically the microphysics included in white dwarf models gets more and more uncertain. We have to make more and more assumptions about things. So essentially, more work needs to be done for cooler models, so we're aware of this. There is actually ongoing work happening right now. There just so happens at Warwick that 3 projects all happened this year have found the same result. There was some work to do with COS as well that found this too. So essentially what you can do if you don't want to include that, you can get the models, you can cut them to not include that if you so wish. But this still would work all right as a standard. But yeah, there is going to be, there is work happening right now for cooler white dwarf models. So I would say just sort of watch this space for the next couple of years.
Yeah, John Deb, Space Telescope Science. First of all, fantastic talk. Really love seeing all this pretty white dwarf work. Are there plans to then extend these to JWST wavelengths?
Yeah, so these are all available to JWST wavelengths. So yeah, this goes from, so these models go from 912 angstroms to 32 microns. I didn't show that on the plot because obviously we've already got data there, but we've got the models for all of that. So basically goes to, yeah, wherever Carl's reddening function went to. Yeah, 32, yeah, because when I tried.
You plan to observe them as well, just as you've observed them in the optical linear infrared.
Yeah, so I didn't do it this cycle because I ran out of time because I was doing other proposals for ESO. But yeah, so essentially I wanted to figure out where the flux calibration community was this year and what sort of work is going to be done. And then hopefully we'll put in a proposal next year that will be really compelling for a sample, all 17, hopefully, fingers crossed, if they want to give us time for all 17. But yeah, we would ideally love some JDOST time for these.
I can be loud. Thanks for a great talk. I was wondering if you could just maybe bound the range of AV magnitudes that this sample of 17 objects might be at, say, J or H or K.
I don't have that off the top of my head. That is in the paper. There is a table with all those bands in. But I can tell you for the Gaia G magnitudes, these are all between 12 and 14 mag. The current primary standards are around 13, and the fainter axelrod standards are around 17 to 19. So I feel like with the way things are going, like we were talking about earlier in the week, we want many, many standards, right, that are spanning lots of different temperatures, lots of different magnitudes. So for any body science, you've got a standard in CalSpec that you can just choose. I feel like with these cooler ones, with the fainter ones, with the primary standards, we're getting there to span all of the magnitude ranges. But yeah, there's lots of different magnitude ranges in the paper.
Last question. You mentioned that there were 3D effects included in the models, right?
3D convection, yeah.
Could you quickly highlight the effect of those effects? And what would happen if you included the non-entity?
So yeah, so for 3D convection, that is important to account for especially for the UV below 13,000 Kelvin, I believe it becomes important. So like if you don't include 3D convection effects for models below 13,000 Kelvin, you start to get into issues. So it's more precise for those. And for non-LT effects, they're only really noticeable less than 40,000 Kelvin in high resolution bar-malign cores. So it really doesn't matter for these ones, but LT is the way to go for like the most precise if you want.
Let's thank our speaker again. So we now have a coffee break. Come back at 10:30. Be sure to see the last 5 posters by Ellen Baines, Susanna Joyce, Peter Nemeth, David Rubin, and Prasenjit Saha.